In this section, we're going to learn the chain rule. Now, in Theorem 4 is sort of the generic statement, the most general form of the chain rule. The chain rule will be, with us, will be an important part of differentiating functions, just about all functions. We'll kind of use the chain rule at some point. And what the chain rule does is it extends the rules that we already know how to use. All right? So the chain rule at first just looks like an example of like simplifying, a fraction, multiplication problem. Like dy dx is dy du times du dx. It's almost as if we're just saying, oh, cancel the du, so we get dy dx. So you can sort of see, in a sense, like how it seems like that should be true. It's very believable. And the way that we use it is we say, suppose y is some function of u, but u is some function of x. It helps us differentiate compositions of functions. So if y is a function of u and u is some function of x, which is what we're stating right here, then y is f of g of x, right? So we can think of y as a function stuffed inside another outside function. And if I want to differentiate y with respect to x, I'm just going to take the derivative of y with respect to u and multiply it by the derivative of the inside function. That's what this says. So the way that we're going to encounter it is it's going to help us extend the power rule. So remember, the power rule is the one that says if I want to take the derivative of x to the n, right, we use it to help us differentiate polynomials without having to set up the limit. So we just had to bring the n down, bring down the power, and then we reduce the power by 1. Now, the chain rule helps us out because what if I don't just have x to a power? What if I have stuff to a power? And that's what we have down here in Theorem 5, the general power rule. So y is equal to u to the n. So maybe it's not just x to the n. Maybe it's a bunch of stuff. It's a whole function of x raised to the n power. Well, the general power rule says that I can just use the power rule like I normally would. That's what that says, right? N times u to the n minus 1. I could do it as long as I follow up by multiplying by the derivative of the stuff inside, right? Derivative of u. This right here is us applying the chain rule. So, in essence, what we're doing in this section is learning how to extend the power rule so that we can take the derivative of something that looks like this: stuff raised to the power of n. So let's do an example. We're going to do this first example twice, okay? We're going to do it first by identifying the u and sort of using the notation in Theorem 5. And then we'll do it again kind of the way that I just imagined, the way I think of it every time I do a problem like this. So we could rewrite this function as a composition of two functions where I could think of y is really u to the 7th power, right? It's stuff to the 7th power, so I'm going to think y is u to the 7th, where u is 3 minus 5x squared. So to take the derivative dy dx, this is going to be dy du times du dx. So dy du, if I take the derivative of this with respect to u, that's 7 times u to the 6th power. And du dx is, let's see, if we use the power rule on that, the derivative of 3 minus 5x squared is a negative 10x. And then the only thing left to do is to say, well, since u is 3 minus 5x squared, I'm going to just substitute that back in. And then the last thing is let's simplify. So I'm going to gather my coefficients in front, I'll call this a minus 70x times 3 minus 5x squared to the 6. There's our dy dx. So we can identify kind of the outer function is stuff to the power, right? Y equals u to the 7th, and my inner function, my u, is 3 minus 5x squared. Now when I introduced this problem, I said we're going to do it twice, and we are going to do it twice. So right now I'm just going to rewrite this function, 3 minus 5x squared to the 7th. And when we use the general power rule, I just think, okay, I've got some parentheses to a power. I want to use the power rule. So I'm just going to go ahead and do it. I'm going to say, all right, I've got stuff to the 7th. I'm going to bring the 7 down. So dy dx is 7 times. I'm going to rewrite this as is, no changes. 3 minus 5x squared to the 1 less power. So there's me using the power rule on that. But what Theorem 5 says is that I can do that as long as I remember to multiply by the derivative of the stuff inside. And that's going to be a negative 10x. So what kind of took us several lines and setup, we can kind of do all in one go, so that now we have the, we still have the simplification, but you could see it's a little bit quicker to do it this way. It's okay to do it either way, whichever of these ways appeals to you, as long as we correctly apply the chain rule in helping us find this derivative. So this, if we look at just this example, the chain rule has allowed us to find this derivative by doing a lot less work, right? It's not that in this particular function, I suppose we could have gone at it by doing a whole lot of algebra to expand 3 minus 5x squared to the 7th power, right? We could write out Pascal's triangle to the 7th row. We could do a lot. It would still, that work would cover a page, I'm sure, to kind of figure everything out. And then when we found the derivative, it would be in an expanded form, which is usually not that useful. Like having a derivative that's in a factored form is really desirable. So the chain rule is super important. It made this derivative a whole lot easier than it would have been, and it makes some derivatives possible. Like sometimes we don't have the algebra that's at our disposal that would help us rewrite it in a way that would turn it into a polynomial. Not every function's a polynomial. Now we're going to do another one here. Here's a problem where we're going to combine, this basically combines the chain rule with a product rule. Now you're going to see that there's a bit of algebra to do. It's going to seem a little bit complicated, but the way the algebra works is always the same in all of these, so once you do a bunch of practice, you'll kind of develop a rhythm to these types of problems. So back when we were learning about the product rule, you'll recall, the first step in using the product rule is recognizing that you need to use the product rule. I have a product, right? I'm multiplying two things and they both have x's. So we need to apply the product rule. Our f function will be 3x squared. So f prime is 6x. Our g function is 2 plus x to the 4th raised to the 5th power. And to find g prime, we're going to need to use the chain rule. So you might want to pause the video and see if you can't work it out before I go ahead and explain how I'm finding it. To get g prime, we're going to bring that 5 down. We rewrite the stuff in the parentheses as is to the 1 less power, so to the 4th power, and then apply the chain rule, multiply by the stuff inside, the derivative of the stuff inside. So times 4x cubed. And we can clean this up a little bit. That'll be 20 x cubed times 2 plus x to the fourth all to the fourth power. There's our g prime. Alright, so this is some side work. Now we're going to go over here and find our derivative, r prime of x. Let's see, the product rule goes g times f prime plus f times g prime. Now I'm just going to plug in the expressions over there on the right. So g times f prime is 2 plus x to the fourth all to the fifth power times 6x plus f times g prime is 3x squared times 20x cubed 2 plus x to the fourth all to the fourth power. Alright, so what we have written here is equal to r prime of x. It is equal to that derivative. However, it is very, very unsimplified. This is not where we want to leave it. Failure to attempt to simplify a problem, a derivative like this, just stopping at this point will probably result in a score of 2 on that math rubric. So we want to get it in a nice, useful form. Let's see. I'm gonna just clean things up a little bit first. Not a whole lot to clean up. I guess the only thing I might do is before the big simplifying step is rewrite this second term. So that's 60x to the fifth and then 2 plus x to the fourth. So here's the step that's always going to be the same. Anytime you're doing finding a derivative in a scenario where you need to combine the chain rule with either the product or quotient rule, you have an algebraic step where you're going to take out the greatest common factor. In this case, maybe you want to pause the video and see if you can't identify the greatest common factor before I describe it. For our greatest common factor, we certainly have for constants, a factor of 6, and we have a factor of x. Also, they both have in common this parentheses raised to some power, right? The 2 plus x to the fourth. The difference is one of them is raised to the fifth power, and in the other it's raised to the fourth power. The rule is you always take out the least power. So we're going to add in a factor of 2 plus x to the fourth to the fourth. This is the crucial step here when we're simplifying these derivatives. So now we're going to see, what do I multiply by, what are we left with, right, when I take that out? So what would I multiply by this stuff here that I just took out in order to get this expression here? So we've already got the 6x because we took that out. The difference, though, is that we need the fifth power and we took out the fourth power. So we're going to need just a 2 plus x to the fourth to the first power. I'm going to leave off the raised to the first power, but that's all we need. In the second term here, we've already taken out the fourth power, that parentheses to the fourth power. So this part's all set. We took out a 6x, and so to bring us to 60x to the fifth, we'll need a 10x to the fourth. And what's left to do for this problem is just simplify what's in the brackets. So that's 2 plus 11x to the fourth. Alright, so this product right here, that's our derivative. That's our simplified derivative. It's in a nice, neat, factored form. Alright, what's great about the general power rule is that we're not limited to integer powers. The way we've been applying it so far has really just been to polynomials, so positive whole number exponents. But you can apply it to negative exponents and rational exponents. So we can use it to help us find the derivative of the square root of x squared plus 1. So the first thing I'll do is write it in a power rule friendly form. So the square root I know is a 1/2 power. So we got x squared plus 1 to the 1/2 power. Now we can apply the general power formula. dy dx is equal to, we're going to bring that 1/2 down, rewrite the stuff in the parentheses as is, x squared plus 1 to the 1 less power. If I subtract 1 from 1/2, I'll get negative 1/2. And then we follow up by multiplying by the derivative of the stuff inside. We got to use the chain rule, so times 2x. That's equal to the derivative. Now we want to simplify. We can cancel the 1/2 with this factor of 2. So we could write it as x times x squared plus 1 to the negative 1/2. I'm going to go ahead and write it. You'll notice they use radicals and not rational exponents as when they gave the function. So I'm going to go back to radicals. I'm going to call this x over the square root. Right? It's a negative 1/2, so that's a square root in the bottom. So x divided by the square root of x squared plus 1. All right, let's try another one. This one, there's more than one way you can approach it. Maybe you want to pause the video and see what you think can be done to help us differentiate this. So I'm going to rewrite this. You could do this in a couple of ways. Now the cube root is a 1/3 power, so you could think of this as x squared to the 1/3 power. But I'm going to rewrite it. I'm going to go one step further. You could take the derivative in that form and just follow up with the chain rule, right? Because we'll have to multiply by the derivative of x squared. But we could actually go make it a little bit simpler. Raising a power to a power, we could write that as a single exponent. So we have 4x to the 2/3 power. And now we actually don't need to worry about the chain rule. dy dx is 4 times, now I'll apply the power rule, 2/3 x raised to the, see, if I subtract 1 from 2/3, I got negative 1/3 power. So we could write this now as 8/3 x to the negative 1/3. But if I want to write it with radicals, which is how they chose to write the function, this would look like 8 over 3 times the cube root of x. All right, let's do another one. We want to find the derivative of this function, 1 over 1 minus 4x to the 5th power. So if you're looking at this, you might have some ideas on how to proceed. A lot of people look at this and they think, oh, the quotient rule, right? Because we have a fraction. And you can use the quotient rule on this. You can use the quotient rule and you'll get the correct answer. But you don't have to use the quotient rule if the top or bottom is just constants, right? The only time we really have to use the quotient rule is when we have variables in both the numerator and denominator. So here we can rewrite the function. I'm going to write it in a power rule friendly form. 1 minus 4x to the 5th power in the bottom is the same as 1 minus 4x to the negative 5th power. So there it is in a power rule friendly form. Now we can find f prime of x using the general power formula, making sure that we apply the chain rule, bring down that minus 5, then 1 minus 4x. Now if I subtract 1 from this exponent, we're going to get negative 6, not negative 4. And we're going to multiply by the derivative of the stuff inside, and that's negative 4. So we got 20 times 1 minus 4x all to the negative 6th power, and we can write it again in the form of a fraction, 20 over 1 minus 4x to the 6th power. right, let's do one more. Here we have a function that is in the form of a fraction, and now notice we have x's in both the top and the bottom. So we do need to use the quotient rule here. So when we find dy dx and apply the quotient rule, that looks like g times f prime minus f times g prime all over g squared. I'm going to do some side work here. Our f function is always the top, so that's x. F prime is equal to 1. Our g function is the bottom. And it's as it appears on the bottom, so that's the square root, which is a 1/2 power. 1 minus 4x to the 1/2 power. G prime, maybe you want to pause the video and try to work out that derivative. We're going to apply the general power rule and the chain rule. So 1/2 times 1 minus 4x to the negative 1/2 times negative 4. There's the chain rule right there at the end. We can simplify. So we got negative 2 times 1 minus 4x to the negative 1/2. Alright, so let's put this all together. G times f prime is 1 minus 4x to the 1/2 times 1 minus f times g prime and all divided by g squared. So there's g squared. So, on the bottom we could see pretty clearly, we're going to square that square root, so we just have 1 minus 4x. And then I'm going to clean up the top a little bit before we do our real simplifying, before we do a lot of the work that'll simplify it much further. It'll be a plus 2x minus 4x to the negative 1/2. Okay, so when we were doing two or three examples ago, I guess, we had a problem where we were combining the chain rule with the product rule. And we had this sort of algebraic step, and the same thing happens when we combine the chain rule with the quotient rule. Now, first of all, before as we're looking at this, resist any urge to cancel over addition. We cannot cancel a 1 minus 4x because we don't have a factor of 1 minus 4x, at least not yet. What we need to do is factor out the greatest common factor. And the greatest common factor is just going to be, I guess the only thing they have in common is the 1 minus 4x here. But their powers are different. Right, so here's the 1/2 power, and there's the negative 1/2 power. The rule is you always take out the least power. So we're going to take out a 1 minus 4x to the negative 1/2 power. So on top we've got 1 minus 4x to the negative 1/2. Now we have to figure out what goes in these brackets. So what do we multiply by 1 minus 4x to the negative 1/2 power to get 1 minus 4x to the positive 1/2 power? Keep in mind that those exponents differ by 1. And so what that means is that we just need a 1 minus 4x just to the first power. This is always the case in these problems where you're combining the chain rule with a product or quotient rule, because of how these factors come out, because of how we kind of put together these pieces, right? In one of those terms I'm taking the derivative of g, and then the other one I'm not. Like by necessity, those powers are going to always just differ by 1. So if we multiply this by 1 minus 4x to the first, and it might help to actually see it like that, written out like that, that would actually, if I multiplied that, that would give me the positive 1/2, because we'd have to add those exponents. Then I bring down the plus, and what do we multiply by 1 minus 4x to the negative 1/2 to get this? Next term, well, I've got that part. I've got the 1 minus 4x part because I took out the negative 1/2 power. We just need to pick up the factor of 2x. Now we can go a little further. I'm going to bring this down. Now write that to a positive 1/2 power in the bottom. And up top, we've got 1 minus 4x plus 2x. That's 1 minus 2x. And now we're just about done. I'm just going to simplify the bottom because, of course, we have the same base, so we can add those exponents. We get 1 minus 2x over 1 minus 4x to the 3/2 power. And that's our dy dx. Now we're almost done this problem. They just, at the end, they asked us to evaluate it when x is negative 2. So let's plug in negative 2. So that's 1 plus 4. We get 5 on top. At the bottom, we get 9 to the 3/2. That's the square root of 9 is 3. 3 cubed is 27. So 5 over 27.